Likewise, when the sound enters the oval window and travels down the length of the basilar membrane, whatever frequency components are present in the sound itself cause individual fibers to resonantly vibrate. And this is a way in which the basilar membrane can actually begin to decode the music. It's absolutely brilliant. Today we're going to talk about the human ear. We are now at a point where we're talking about the third of the 3 Ps that I reminded you of earlier: the production of sound by way of vibrations, the propagation of sound by way of the movement of that sound wave through the air. And finally, today we're going to talk about the perception of sound, the ear's ability to process that sound and turn it into something that we can appreciate specifically for the purpose of music. The ear consists of 3 basic components: the outer ear, the middle ear, and the inner ear. And I'm going to go through each one of these now and tell you about the purpose and function of those. Then we'll talk a little bit about how the ear actually is able to discern individual pitches, which is very important for the enjoyment of music. The outer ear consists of the auricle, the auditory canal, and the tympanic membrane. The auricle is this large cartilaginous structure outside our head, and it has kind of a funny shape, but the shape actually does serve a purpose. And later we're going to talk about binaural perception, the ability to locate things in our environment by our ears. And the earlobe, the shape of the earlobe actually has something to do with that by the way that it funnels sound into our ear. And one way you can test for that is you can put your hand behind your ear and cup it, put your thumb behind the ear and cup it. You don't have to do that now. And when you do that to both ears and pull it forward slightly, listen to your own voice, and you'll hear it really amplified. And you'll also hear it in better fidelity, because when we hear our own voice, we're hearing it through our skull rather than through our ears. And when you cup your ears and amplify the auricle's ability to do that, you can tell that its purpose is partly to do that. It's a much larger surface area, so it collects more sound than the auditory canal would receive. Once the sound is projected into the auditory canal, it terminates at the tympanic membrane, and that represents a closed-ended tube. The tube's about 2.5 centimeters long, and since it's closed-ended, one end is closed, then we know it supports odd harmonics. And it turns out for that 2.5 centimeters, the first resonance of that semi-closed tube is around 3,500 to 4,000 hertz, which is a very important frequency for human perception, human audio perception. For one thing, it helps us discern speech, because the formants that form the components of spoken vowels shift, and our ear picks up on the location of those formants, and that's how we hear the vowels that we do. So the resonance of that tympanic, or the auditory canal, is actually well suited for frequencies that are important to us. Now, when the airwave, the audio wave, comes into the canal and impinges on the tympanic membrane, what I want you to realize is that the waveform of that sound, the very complex waveform, which we've talked about in the propagation of sound, causes the tympanic membrane to vibrate in sympathy. So the vibration of the tympanic membrane mimics or matches the variations in sound in the waveform itself. And then it passes it on to the middle ear. So the outer ear then is the auricle, the canal, and the tympanic membrane. The middle ear consists of 3 small bones called ossicles. They're the smallest bones in the body. They're named the malleus, the incus, and the stapes, and they transmit the vibrations from the tympanic membrane to the oval window, which is the entrance to the cochlea. And in that way, they cause pressure waves to flow down the fluid inside the cochlea. Now, the fluid inside the cochlea is dense. It's much denser than air, and so when the vibrations that are transmitted by the ossicles hit upon that liquid, the amplitude inside that liquid is actually very tiny because it has a lot more inertia. And so there's a natural mechanism by which this middle ear amplifies the sound. It's really, truly amazing. And I'll talk about that in just a moment. And then the inner ear consists primarily of the cochlea. The cochlea is a very, very small, it's about the size of a pea, and it's a very small organ that's coiled in on itself and contains the means by which the frequency spectrum of that sound can be decoded. So on the next slide, we see a close-up view of this region. The malleus, the incus, and the stapes right here in the middle ear transmit vibrations from the eardrum to the oval window. And the amplification happens in the following way. We've talked about pressure. We've talked about pressure, the definition of which is the force per unit area. Since the tympanic membrane exerts a force on the malleus, the incus, and the stapes, that force is transmitted right on through to the end. Because of the fact that a force applied to a body is met by an equal and opposite force, the force that's applied to that first bone is the same as the force that's applied at the window. However, the area of the tympanic membrane is about 55 square millimeters compared with about 3.2 square millimeters for the oval window. And because pressure is ultimately what corresponds to the sound, it's a pressure variation, the force divided by the area here at the tympanic membrane provides a much smaller pressure because it's divided into a much larger area. The pressure is much higher by a factor of about 17 because we're going from a large surface to a small surface. So that's one means by which the ossicles can actually amplify the sound. And the other way is by virtue of the fact that these two bones form a lever. And there's a bit of a lever advantage that amplifies the sound a little bit more, so that by the time the sound gets to the cochlea, the pressure variations have been amplified by a factor of about 22. And this is a non-powered amplification. This is just a natural amplification by the design of the ear, which is an absolutely amazing organ. Okay, and then the inner ear receives those vibrations and travels down the length of the fluid. It fills the entire length of that cochlea. And we'll talk about the cochlea in just a moment, but it's what decodes the sound into its components. Okay, in the next slide, you see, okay, so actually let's back up to the last slide, the previous one, because one thing that we need to know about the cochlea is that it's actually divided into 3 chambers. If you look at a cross-section of the cochlea like this, there are 3 chambers, but there are 2 main chambers that are divided by a very thin membrane called the basilar membrane. The basilar membrane is where the decoding of sound occurs. And you can imagine that it's a flat membrane that it runs along the entire length of the cochlea. And so in the next slide, I've got a depiction of that basilar membrane stretched out. The total length of the cochlea is not very long. It's, as I said, coiled up, it's about the size of a pea. At the entrance, at the oval window, which is on this side, there are very small fibers that run across this basilar membrane, about 20 to 30,000 of them, from the beginning to the end. And the ones at the very beginning are sensitive to high frequencies. If you think of these as strings on for example, strings on the soundboard of a piano, different strings have different resonant frequencies, and it's the same here. These 20 or 30,000 fibers across the basilar membrane actually each have an individual resonant frequency. I don't know if you've ever done this before, but one thing you can do with a piano, for example, is you can hold the pedal down so all strings are able to vibrate, and then play a sound, like from a flute. And when you play that sound from the flute and stop, you'll hear one of the strings of the piano vibrating in sympathetic vibration with that sound. In other words, the sound waves from that flute set one string into vibration because of its natural frequency. Likewise, when the sound enters the oval window and travels down the length of the basilar membrane, whatever frequency components are present in the sound itself cause individual fibers to resonantly vibrate. And this is a way in which the basilar membrane can actually begin to decode the music. It's absolutely brilliant. The front of the cochlea, which is at the oval window, receives the very highest, or interprets the very highest of frequencies that we can hear. And then down at the very end of the basilar membrane, when it's wider and the fibers are thicker and have less tension, it's sensitive to the very lowest frequencies we can hear. So from the oval window all the way to the end, we have the perception of frequencies of around 20,000 hertz all the way down to the end. And because the very first part of the cochlea to receive sound is at the high frequency side, this is why when old age or exposure to very, very loud sound causes degradation of the high frequencies. That's the first to go when you start becoming, when your hearing system starts degrading. It's the high frequencies that go first, and that's because the barrage of sound coming into the cochlea is highest in amplitude right here at the beginning. Then those fluid waves, this entire thing is immersed in a fluid. The fluid waves travel down the length, and by the time they get to the end, they're actually reduced quite a bit in amplitude, which is one of the reasons we don't hear low frequencies as well, and we actually have to amplify them, especially when the overall volume of music is low. Okay, so on this diagram, I've shown you a sine wave, a pure tone of relatively high frequency. You know, it's going to be around a couple of thousand hertz, for example, if this goes from 20,000 down to 20. And what I have here is the sine wave that's entering the ear, and then what we could envision as a frequency spectrum for that sine wave tone. This effectively is a frequency spectrum. It's quiet, except for that one frequency, and that one frequency corresponds to the resonant frequency of this cluster right here of fibers across the membrane. And so when this sound enters the ear, it activates the vibration of just that narrow region of the basilar membrane, and the basilar membrane is then up against some very, very small little hair cells called cilia that get tickled when the membrane vibrates sympathetically with that vibration. These nerve cells, or these nerve hairs, pick up that vibration, send it down the auditory nerve to the brain. And so because this particular cluster of strings vibrated, or fibers, the brain receives the information that that vibration occurred, and therefore that this tone had that particular frequency. If I change the frequency somewhat on the next slide, we have a slightly lower frequency. You can see the longer wavelength here, and you can see that the frequency peak in the sound spectrum has shifted to a lower value, indicating that when we change the frequency of that pure tone, the basilar membrane vibrates in a different place and therefore sends a different set of nerve signals to the brain, indicating that different pitch. And in the next slide, we have a lower frequency yet. In the next slide, and here's a very low frequency, long wavelength. And so you get a sense of how, along the length of the membrane then, individual frequency components of a sound will activate different regions of the basilar membrane. So in the next slide, actually, we have the sound wave from a nylon guitar. I've shown you this frequency spectrum before, but now I've overlaid it on top of the basilar membrane for us to get a sense that this waveform, which is a note from a nylon guitar, has this particular sound spectrum which stretches across the membrane from low to high frequency. And so you can imagine these spikes right here, which correspond to this particular sound at this particular moment, are present in this waveform, and they activate regions of the basilar membrane at those spots, at those locations. So now the basilar membrane is vibrating in lots of different places all at once, and what we perceive then, what's sent to the brain, is this fundamental pitch, and then all of these harmonics, which are integral multiples of that fundamental as well. So the brain receives several vibrations all at once and can then understand and interpret that in terms of the sound that's being transmitted, in this particular case, a nylon guitar. And let me just remind you that the guitar, the personality of the guitar is inherent in the frequency spectrum itself. The particular locations of the harmonics and their relative strengths give us, ultimately, the perception of a fundamental tone, and then these harmonics give us the timbre of that nylon guitar. So if we hear it, we can recognize that that's a guitar and not a flute because of the presence of these higher harmonics. And so the basilar membrane does this wonderful job of effectively it's a frequency decomposition activity where it actually decomposes this sound wave into its frequency components and sends them off to the brain. It's a little bit analogous, if you think about it, to an analog to a digital conversion. This is an analog waveform, and this is effectively a digital set of information because its frequency is located in particular places in the spectrum that are each vibrating independently and sending that information to the brain. So on the next slide, I'm going to speak briefly about now the range of human hearing. As we look forward to material that's coming up, we're going to understand how the ear interprets not only the complex waveforms that we have in nature and in sound, but how it varies in its ability or sensitivity to different frequency ranges. The lowest end of the frequency spectrum for a young adult is around 15 hertz. That's a very, very low frequency, and it's about the location of the very bottom musical notes. There are instruments that play very, very deep notes, like the bass bassoon or the organ can play extremely low notes below the bottom of the piano. And so 15 hertz represents the very lowest end of our frequency spectrum we can hear. 20,000 hertz is about the top for, again, a teenager at the peak of the sensitivity of the ear, goes up to about 20,000 hertz. We don't hear that as a pitch. We only hear pitches up to about 8,000 hertz. So actual music resides in the realm from about 16 hertz to about 8,000 hertz as far as melody goes. However, it's very important that we have the rest of this available to us because that's where the harmonics of these tones are. If I play a high note on a piccolo, for example, or a very, very high note on a violin, one of the harmonics on the violin, then I hear a pitch right here. But if we stopped right there, if that's all our ear heard, we would be missing all of the harmonic component which resides up here, and therefore the ability to discern timbre. And so all the way up to 20,000 hertz is useful in our ears for discerning music, especially if we want to enjoy it, because it's very important for the fidelity of the music that we be active up here as well. Now, there is an infrasonic range, and that infrasonic range below the bottom of the frequency spectrum for the ear is a realm where we don't actually hear sound, but if it's loud enough volume, we can feel it. You've probably all had the experience of being at a concert, for example, where there's a lot of deep bass, and you can actually feel that thumping in your chest. Well, once the frequency drops below about 15 hertz, we can feel it, but we can't hear it. We don't hear it as a pitch anymore. So the very bottom pitch that we can hear is around 16 hertz. Now, we have also learned about beats. When we combine two tones of very similar frequency to one another, those beats that are produced occur anywhere between, say, 1 and 15 hertz, depending on how close those tones are. So what you did in lab in producing those beat waves, you were able to listen to those beat waves as a repetitive pattern that didn't itself produce a pitch. The beat wave is such that we hear a pitch, we hear a tone, but that tone is modulated on and off at what we call the beat frequency. Now what's interesting is that also resides in the infrasonic range. The beat frequencies for two tones that are close to one another they don't produce music or pitch, but they produce a variation in loudness between those two tones. However, as I separate those two tones to be further and further apart, the beat frequency goes up, because remember, the beat frequency is the difference between those two, and eventually we pass the 15 hertz boundary. So if we take two tones and listen to their beats and then separate them out, we will begin hearing them as, well, for one thing, we start off hearing them fused together because we can't discern the difference between those two pitches that are very close to one another. But then as we move them out, we start discerning two separate pitches. But the magic is also that the beat waves, which were present down here as beats, start becoming too high in frequency for us to hear as beats, and we begin hearing them as actually a tone, a third tone. So there are two tones that are producing it and a third tone, which we call the combination tone, and that actually becomes part of tones that we perceive in the brain, and that also is very important for the perception of music. In the ultrasonic range, we have frequencies that are too high for us to hear. The human ear has a limit of 20,000 hertz, but there are some animals, including dogs, for example, that hear well into the ultrasonic range. Okay, so on the next slide, I have an interesting philosophical issue to bring to your attention, and that is we have this thing called frequency, which is something that we can measure with instruments. We can measure in an absolute way. We can measure time, and we can count how many beats occur within a certain time. And so that frequency is what we call an absolute measure. We have instruments we can use to measure it. So far, we have talked about the measurement of the loudness of sound too in terms of intensity. And intensity is measured in watts per square meter. We've also developed a tool called the sound level, which allows us to take that very large range of intensity and shrink it down to 120 decibels to represent the range of loudness that the human ear can hear. Here's the frequency that the human ear can hear. This is actually the frequency corresponding to the keyboard. But we also have a difference in the perception of loudness from low tones to mid-tones to high tones. We'll get into that in chapter 8, in the next chapter. But right now, as far as the frequency perception goes, this is something we measure with instruments, but we don't actually hear frequency. What do we actually hear? We hear pitch, right? Pitch is now it may not really seem like a psychological issue, but pitch is really a psychological perception of that music. And I'll explain that in the following way. The analogy is light. When we look at visible light, and this is not something we've talked about, but light from the red end to the blue end really represents a small range of frequency for electromagnetic radiation, which is light. From the blue to the end spectrum, there's about a factor of 2 in the wavelength of light. But in going from blue to red, it's a continuous change. It's just like if I have a sine wave here, and I simply compress that sine wave by a factor of 2, that's what I'm doing in going from red, which is a long wavelength, down to blue. Now notice, in doing that, the waveform itself does not contain any information about color. It's just a frequency change from one frequency to about half that frequency. But the way our brain interprets that color, or that frequency change, is as colors. So we see red, orange, yellow, green, blue, indigo, and violet. Those are the colors of the rainbow spectrum, or of the spectrum. And we see those if we've got color vision, which not all of us have in full force. But it's a psychological perception of light. And it's much more familiar to us than sound is. But if we look at that analogy of light, that similar situation, we recognize that there's something about the perception of that light and the processing by the brain that produces this extra dimension we call color. Now, as far as sound goes, we actually use the word chroma to determine or to describe the variations in pitch that we hear and the different colorations that we receive as a result of those different pitches. Pitch is a psychological phenomenon. We divide pitches up, at least in Western music, up into 12 tones. And those 12 tones span what we call an octave. So in going from the lowest C on the piano up to the next C, we change what is called chroma as far as pitch goes. We change that chroma from whatever chroma value that C would have through a range of notes. And then we come back to the C. As a circularity, we come back to C, and we have the same chroma, except it has what we call a different tone height. So as we march up the scale, there's this repetition pattern that we have with regard to pitch, which is why we can divide it up into something that's useful for music. The pitch is circular, the frequency is not. And that's where this psychological aspect of sound is very important to recognize. In going from 30 hertz all the way up to 4,000 hertz is just a continuous change of frequency. However, and it's just a variation that has no demarcation between any note values, but our perception of that is that we perceive it, a C and a C sharp and a D to have different coloration or different pitch. And furthermore, there's this circularity where we come back to, over and over again, C in the scale. And so we've developed this notion of chroma, which represents the different coloration of different notes, but then tone height, which represents or describes the fact that we've got this circularity to pitch. We're going to talk more about this in chapter 14 when we talk about musical temperament. But I want to indicate to you that this pitch is something that we don't really fully understand, as we don't understand coloration. We can talk about it. We can talk about the visible apprehension of color in terms of the stimulation of nerve cells in the brain, but the actual experience of seeing red or blue or green is a mysterious one. And it has to do with the brain interprets those light waves. In the same way, there's a mystery as far as how we perceive different pitches based on their color value, so to speak, in terms of sound. And furthermore, as we can with the eye, we can fool the eye with optical illusions. We can do the same thing with sound. We can actually fool the ear by juxtaposing pitches and using things like masking to change the way we perceive music to show us that this is a bit of a fluid perception. Now, some of us have perfect pitch, and it would be interesting to know whether people with perfect pitch could be fooled by the same kind of audio illusions. But the main point here is that pitch and frequency are two different things. Frequency is something that we measure with instruments. Pitch is something that gives us the richness of music. Okay? So let's go back a few slides and go back to the ear, right? A few more, right here, stop here. Okay, so in this small canal then is what is analogous to frequency. It's simply the high frequencies at the opening, the oval window, down to the very lowest frequencies, and this bundle of cilia, the cilia that sense the vibrations of that basilar membrane, pass nerve signals down the auditory nerve, and so all of this processing of sound that I'm talking about from frequency into pitch happens as a result of the brain's interpretation. The ear does nothing to determine pitches. All it does is very faithfully send off a frequency spectrum of a collection of vibrations corresponding to that tone into the brain, and that's where the actual processing of that tone occurs. Likewise, because the basilar membrane vibrates from the highest frequencies in a continuous and linear fashion down to the very lowest frequencies, we talk about this as a tonotopic organization. The basilar membrane is tonotopic in the sense that it has a very linear progression of frequencies to which it maps. That tonotopic arrangement on the basilar membrane is actually mirrored in the brain. So scientists have followed the auditory nerve into the center of the brain, the auditory cortex, which for the right ear is actually processed on the left brain, the left lobe, and for the left ear is processed on the right lobe. So when the signals come from the auditory nerve into the brain, they cross through the brain over to the auditory cortex, and the auditory cortex is also laid out in a tonotopic fashion. So if you look at the way the signals eventually reach that auditory cortex, there is a linear progression from the perception of the lowest to the highest frequencies. Very, very interesting mapping of the cochlea onto the brain. Now, there are issues of fidelity that eventually set in when the ear ages. When the tympanic membrane starts becoming stiff with age, there are extra distortions that start entering in, but it's also less flexible to vibrate over the entire frequency spectrum. And this is one of the reasons why with age comes a diminishment or a diminution of the ability to hear the entire frequency spectrum. Likewise, these bones can become, as they age, they can become less stiff. There's little ligaments that connect them, and those ligaments also age and get a little bit stiff. So the fidelity of music starts going down with age because the tympanic membrane limitations and the bones. And then finally, as we've just mentioned, since very, very loud sound assaults the fluid of the cochlea with very high amplitude variations, the nerve cells at the very beginning here die out more quickly than the nerve cells at the very end. So we retain our ability to hear low frequencies well into old age, but the high frequencies start going. And of course, You don't live in the era of tube televisions, but when I was a kid, I would walk in the room while my parents were watching TV, and it would have this high frequency pitch that was really annoying, because that's what tube TVs do. As the tubes get old, they put out these very high frequencies. And I would walk into the room and I'd say, Mom, Dad, how can you listen to this TV with that high pitch? And of course, they couldn't hear it, because as a natural consequence of aging, the high frequencies for them were diminished in their sensitivity, and they couldn't hear that. Likewise, if you expose yourself to too much loud music, you can do damage at an early age, and that damage is not actually repairable. However, there is a technology that's starting to develop, and we'll get into this when we talk about the recording and playback of music and we look at the electronic aspects of music. There are cochlear implants that are available, and they're becoming more and more sophisticated in their ability to replace the basilar membrane with a device that can be inserted into that cochlea and effectively pick up the vibrations at different frequencies and send them onto the brain. It's an absolute miracle that the technology exists, and it's starting to become more and more sophisticated. The very earliest of these cochlear implants could only have about 5 sensors, one here, 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 just a few along the length, because it was hard enough to get it in there and reduce the electronics of that little insert down to such a small scale. Nowadays, they're developing cochlear implants that have many, many hundreds of sensors that can start giving us the perception of the variations that we need to enjoy music. It's still a long way from being able to give us the highest fidelity that the ear has, but in time, the limitations of the ear may be overcome by technologies in a way that we can retain the full spectrum of sensitivity well into our old age. Okay, so let me just summarize then. If we go back one more slide, I'll just summarize the main components of the ear. The outer ear is the one that collects and sends the sound down the canal and impinges on the tympanic membrane. There are also surgical procedures to repair tympanic membranes or eardrums if they get damaged. If you put something in your ear and you poke it, you can actually break the eardrum, which makes it inoperable for the hearing of sound. But they've got the ability now to produce synthetic eardrums and replace them. So the outer ear then collects the sound. The middle ear passes it on to the cochlea, but the important point to remember about the middle ear is that it appropriately amplifies sound so that we can hear it with good sensitivity. Because in going from air to fluid, there's a huge reduction of sound, the amplitude of the pressure variations that would cause the ear to be very insensitive were it not for the amplification in those bones. And finally, in the inner ear, we've got this beautiful frequency decomposition device. It's like a fast Fourier transform on the spot. It's transforming waveforms right into their frequency spectra and sending them off to the brain. And the last thing that I will mention is the semicircular canals, which are also part of the inner ear. They have nothing to do with the perception of sound, but they have to do with balance. There's fluid inside these semicircular canals that rotate. As we rotate our head, they change the level, and that sensor is also sent to the brain and gives us a sense of balance.